Today we are going to talk about shared memory consistency models, and just to motivate why we need these consistency models, consider the sequential code, right? It sets flag 1 equal to 1 and then it checks if flag 2 is equal to 0, then it does something, right? Let's say it prints hello, right? Now when you give this to the compiler, right, when this code is compiled, one of the things that the compiler generally does is reorganize the code, right, to make it more efficient. So let's say that you set x equal to flag 1 just before this instruction, and then you execute flag 1 equal to 1. So what will the compiler do? So over here, as you recall, right, typically instructions are pipelined. So what is it going to do? It's going to load the value of flag 1 at some point in time, right, and store it into x, right? But a load has to happen, flag 1 has to be loaded. And now in the next instruction we are saying that flag 1 is equal to 1, right? And now over here it can't change the value of flag 1 until that previous value of flag 1 has not been assigned to x, right? I cannot change the value of flag 1. So there are various ways of dealing with this, but one of the things that the compiler will typically do in such a scenario is it will move this instruction later, right? How does that help? So the way it helps is that suppose that this is where in the pipeline, this is where you are going to store the value 1 to flag 1, right? Now you cannot execute this because flag 1 has not been yet copied out, right? So maybe you insert a no op over here, you don't do anything in that cycle, and then in the next cycle you end up doing the store, right? So that the previous value has been taken, right, has been put somewhere else. So there are various such scenarios which occur, and the crux is that the compiler wants to reorganize the code, right? So the compiler realizes that this flag 1 is not being used in these instructions, right? If flag 2 equal to 0, printf hello. So flag 1 is not being used. So it can safely move this instruction over here. It wouldn't change the output of the code, right? So typically when you write some code and when you compile the code, the compiled instructions will not match exactly with the sequence of the instructions that you have specified. The code will be rearranged by the compiler. That's a very normal optimization that all compilers do. Okay, and you need these kind of optimizations, otherwise your code will run very slow. So these optimizations help your code run much faster. So there are loads of things that they do. They do loop unrolling and various other stuff, right? So as far as the sequential code is concerned, I can safely move this flag 1 equal to 1 instruction later and nothing will be disturbed, right? The output will still be the same of the program. Alright, what happens in a parallel code? So now let's say that I have the following code. So it's a race between two processors, P1 and P2, right? So we want to see who reaches the finishing line first. So P1 declares flag 1 equal to 1, saying that I have reached the finish line. Then it checks if flag 2 is equal to 0, that means that the other processor has not reached the finishing line. Then it declares itself to be the winner. Right, so the code is clear. Similarly, what the processor 2 does is it sets flag 2 equal to 1, and then if flag 1 is equal to 0, it prints P2 is the winner. It declares itself as the winner. So what are the possible outcomes of this code if, let's say I was executing it on a single processor. So these instructions may be interleaved in some way, and let's say there is no compiler reordering of the code. How would this code get executed? What could be the possible outcomes? Either P1 wins, right? This is one possible outcome. P1 wins. Another possible outcome is P2 wins. Any other outcome that's possible? So one other possible outcome is no output, right? No output at all. And is this a possible output? P1 wins, P2 wins. Both of them getting printed. No. There is no possible interleaving of these instructions that you can come up with such that both of them will declare themselves to be the winner. Is this point clear? Okay, so this is not going to happen. That's how you're designing this code. This is part of the code of Decker's algorithm for critical sections. So we'll come across this again. Okay, but essentially this allows you to put a critical section code where you are doing the printfs. What does critical section mean? Only one thread is allowed to execute at a time, right? So you can put that code over here where you see these printfs. As long as what's happening, that the moment you set flag 1 equal to 1, the other processor must also see flag 1 equal to 1. The moment you set flag 2 equal to 1, P1 must also see flag 2 equal to 1. So as long as you can ensure that, right, then this algorithm works for critical sections. Okay? So you put your critical section code over here, processor 2 puts its critical section code over here. But in critical section you always want to make progress, so you can always put this in a loop, right? So that's fine. If you fail, you go back and try again, right? So that's a simple thing to have. All right, let's come back to the question that on a uniprocessor, how can it happen that nobody prints anything? So here's how it can happen. So this is the first instruction to be executed, flag 1 equal to 1, right? And then the program gets swapped out and the other program gets scheduled, right? So the other program executes the statement next, and then this statement.
These two codes will be in a single mainstream program.
No. They are two threads running on the same processor, right? So they'll get swapped in, swapped out, or even if they are processes get swapped in, swapped out, right? So here we are talking about shared memory. So let's stick to threads, right? So if there are threads, then processor 1 will get swapped out at some point in time, processor 2 will get swapped in, and so on, right? So then what will happen for processor 2? It checks if flag 1 is equal to 0, and what does it find? It's equal to 1, right? So it cannot enter this condition. Similarly, now control goes back here, and now processor 1 checks if flag 2 equal to 0, again it finds it to be 1, and therefore none of them print. So now the question is that I understand this is the behavior I want, but is the parallel processing system going to promise me that? Now I'm asking the system to follow certain rules. Why? Because if I just compile the code which is running on P1, if I compile it separately, remember, it will see flag 1 is equal to 1, if flag 2 is 0, print P1 wins. So I'm not using flag 1 again, so it might end up moving this flag 1 to later. What happens if it moves flag 1 equal to 1 to later? What happens if it reorganizes the code now? Like we discussed earlier, right? Compilers reorganize code. What happens if it reorganizes code now? P2 wins. That's okay. That's an expected output. So if any of these three occurs, I'm okay. I mean, this is expected output. What is more serious is that this also may happen, right? That's a serious issue. How can that happen? First, this instruction gets executed, right? If flag 2 equal to 0, it's 0. So it's going to enter and print P1 wins, right? And then it gets scheduled out. This program comes in. It sets flag 2 equal to 1, but the damage has already been done, right? It checks flag 1 equal to 0. Yes, it's 0. It's not been set to 1 yet. So it comes and prints this, right? And then finally, maybe at some point of time, this program executes flag 1 equal to 1, right? So you ended up printing both P1 wins, P2 wins. When I'm in a multiprocessor system, I need to be more careful. When I'm writing programs, how is the system going to interpret these programs? Okay? A lot of things happen, right? For instance, there are lots of optimizations. This is getting into architecture, but still, the compiler decides that what variables am I going to keep in registers. Remember, there are these registers which are right next to the processor. and then there's the cache, and then there's the main memory, right? I'm going all over the place. The other caches and this memory subsystem together, they form your memory system, which is consistent. So now what does the compiler do? If a variable is being used very often, suppose I have a loop variable for I equal to 0, I is less than 1000, I plus plus, right? I do something. So in this case, what does the compiler do? Every time it increments I, it's not going to go and write it back to the memory subsystem. It's not going to update it in the memory every time, right? It costs to go and update the memory subsystem. So in that case, what does the compiler do? It keeps it in the register, right? That's where all the operations are happening, and it knows that it has to do a lot of operations with this variable I. It has to increment it so often, right? So it's not going to put it back to the memory or the cache, right? So it's going to keep it in the register. So now the compiler decides what are the variables that it's going to keep in the registers. What if the compiler decides to keep flag1 in the register? Let's go back to the original code, or flag2, right over here. What if it decides to keep flag2 in the register? When it sets flag2 equal to 1, it's not writing it back to the memory, right? And if it doesn't write it back to the memory, then the other process is not going to see that value. So again, this code is going to be incorrect. Okay, but again, keeping variables in the registers is something, you know, that the compiler decides and compiler optimizes. How can we take that away from the compiler? I can't say that just because I'm running on a parallel system, right, you're not allowed to keep variables in the registers anymore because some other process may access it, right? It's a big pain. And then there are other features also. For instance, there are update buffers. When you write something back to the memory, the processor has update buffers. It may not immediately go and update it. It may get updated after some time, right? Again, now if you try to ensure that the update happens before I execute the next instruction, that's a big penalty, right? You're going to lose performance. So all of these are optimizations that the compiler and the system do for you, right? And if you try to enforce that in a parallel system, just because you're writing a variable and now you expect somebody else might read it, so you can't execute any other instruction, you're putting a lot of restriction on the system, right? The compiler and the runtime system. So that's why you need shared memory consistency models. So what is a shared memory consistency model? The memory consistency model of a shared memory multiprocessor that provides a specification of how the memory system will appear to the programmer. So it basically eliminates the gap between the behavior expected by the programmer and the actual behavior supported by the system, right? So it's kind of like an agreement between the programmer and the system that this is how I want you to behave, and the system promising you that this is how I'm going to behave, right? So it's essentially a set of rules that govern how the memory system is going to process the memory operations from multiple processors, right? So it's essentially, as we said, a contract between the programmer and the system, right? An agreement. It's a set of rules using which then you can determine whether you're writing a correct program or not. It also basically determines that what are the optimizations that can be performed for correct programs, right? What is the compiler allowed to do? What can be done at runtime, right? All of that is decided by these set of rules. So this is one of the most basic consistency models. It's called the sequential consistency model. And it's very, very stringent. So what does it say? It says that a multiprocessor system is sequentially consistent if the result of any execution is the same as if the operations of all the processors were executed in some sequential order and the operations of each individual processor appear in this sequence in the order specified by its program. What does it mean? It basically means that if this is my instruction 1, instruction 2, instruction 3, right, of one processor, and instruction 1, instruction 2, instruction 3 of a second processor, and let's say instruction 1, instruction 2, instruction 3 of a third processor, the output that I see should be one of the outputs of interleavings of these instructions with the order of each program being maintained. So what are the possible orders? One possible order is that instruction 1, instruction 2, instruction 3 get executed, and then instruction 1, instruction 2, instruction 3 get executed, and then these 3 get executed. That's one order, but there are lots of orderings, right? Another ordering is that first all the green ones, then blue ones, then black ones. Another possible ordering is that first the instruction 1 and instruction 2 get executed, then maybe instruction 1 of the third processor gets executed, and then instruction 1 of the second processor gets executed, instruction 2 of the second processor gets executed, and then instruction 3, and then instruction 2, instruction 3. Right? It's just an interleaving of the instructions of the 3 programs with their order being maintained. Right? So this is the sequential consistency model. So as you can see, there are lots of orderings. They may produce different outputs, but the programmer has to understand that all these outputs are valid outputs. Okay? So as we just saw, right? So with the sequential consistency model, what is not possible? Both P1 and P2, both of them winning is not a possibility with the sequential consistency model, right? Because that's not a valid interleaving of the instructions as you see over here, right? There is no way you can interleave these instructions and get that output. And why is it stringent? Because the moment I write flag 2 equal to 1, I want it to appear to be visible to the other processor. The moment I write flag 1 equal to 1, I want it to be visible to the other processor, right? I want any updates to be immediately visible because the other processor may access them, right? It leaves no scope for the compiler to do optimizations, right? Very little scope. So here is one problem. Why is it so stringent? So this is a for loop. For I equal to 0, I is less than an I plus plus, and you're just initializing an array to 0, ARR I equal to 0. Right, simple piece of code. So as I said, right, one very common optimization that compilers do is keep certain variables in the registers, right? Whichever ones are accessed very, very often, they just keep them in the registers because it's too costly to go and keep on updating the memory, fetching them from memory and so on, right? So you want to keep it in the register. So what is the problem here with sequential consistency model? It won't even allow you to maintain I in a register. Why is that? Let's say this is getting executed on P1. Can you give me some instructions which if I execute on P2, I may get an inconsistent result, which is not corresponding to the sequential order of execution of all the threads, right? A valid interleaving of all the instructions of the different programs. Print what?
Print any value of the array.
Print any value of the array, okay.
So if up till now the array has been updated, it will show the value 0.
Okay.
Or else it will show a garbage array.
But that's fine, right? That's a valid sequential interleaving. If this code on P2 executes before the code on P1, that is what you'll see, garbage. If this executes after P1, then that's what you will see, 0. So both of them are valid outputs. They correspond to some valid interleavings of the two codes.
You print array of I, so the second thread will use the value of I which is in the memory.
Right.
So it may be some an initialized value or something. So you can print.
But that's fine, right? Because if suppose the interleaving is such that P2 gets scheduled before P1, it will print some garbage, which is fine because that's a valid interleaving. P2 instructions getting executed before P1 instructions. Okay, so let's see a simple example. So let's say I first print the value of, let's say this is an integer, AI, or not even I, let's say A1, right? I print the value of A1. Okay, and then I print the value of I. That's it. How can this go wrong? I might end up seeing 0 over here which means that this instruction has been executed, and when I print I might get garbage or 0. Why? Because what has processor 1 done? It fetched these instructions, it kept I in the register, so whatever it was updating on I, it is not updating the memory, right? So I is garbage in the memory, or maybe it was, let's say it was initialized to 0 in the memory, so its value in the memory is still 0, right? Whereas it has gone ahead and initialized ARR 0, ARR 1, ARR 2 and so on, right? It has initialized all of these things, but the value of I has not been updated in the memory, right? Now these ARRIs are not going to stay in the registers. This is a million values, you don't have a million registers. So these it has to keep on updating in the memory. It has to write these back to the memory, right? So these array values are written back to the memory. And now what does the other processor see? It sees that when it prints A1, it gets the value 0, which means that it has already executed ARR 1 equal to 0, which means I must have already taken the value 1, but when it prints the value of I, it finds it to be 0. Is this point clear? So what is the crux? Again, this sequential consistency model is a very, very stringent model. It's not going to allow the compiler and the runtime system to make a lot of optimizations to the code, to move code around, right? They can't even store loop variables in the registers. So sequential consistency models, though they are very good theoretically, they are not used in practice, right? You can't build systems with sequential consistency models, or you can't build good performing systems, right?